What you see before you right now is the amazing future of the aviation industry. Try to picture it in your mind. You are walking toward your plane at the airport, but something is completely different. The familiar sound of jet engines has been replaced by an almost uncomfortable silence. The characteristic smell of jet fuel has completely disappeared. Instead, you are about to witness the greatest revolution in aviation technology since the dawn of the jet age. Here it is, the Airbus ZeroE. This groundbreaking hydrogen-powered aircraft project has the potential to completely transform our perception of flight. But here's the real shocker. While other manufacturers are still chasing minor improvements to existing engines, Airbus has chosen a completely different path. They're not just building advanced aircraft, they're reimagining the very fundamentals of propulsion systems from the ground up. And the timeline doesn't suggest these dreams are destined for the distant future. We are talking about aircraft that will enter service in the late 2030s or early 2040s. This will happen during the active working lives of pilots who are currently in training. Let's return to the starting point of this story with 3 revolutionary concepts from Airbus that challenge everything we know about aircraft engineering. The first design looked like the most classic design until it was examined in detail. This turboprop model had the capacity to carry 100 passengers over a distance of 1,000 nautical miles. But these were not standard turboprop engines. They were hydrogen-powered fuel cell technologies. Imagine the reliability of a turboprop combined with technology that emits zero carbon during flight. The only thing coming out of the exhaust is clean water vapor. This model targeted regional routes like Amsterdam, London, and Boston, New York, routes where millions of passengers travel each year on old regional jets that consume excessive amounts of fuel. So why start with a turboprop? This is where strategic intelligence comes into play. Turboprops are naturally more economical at the altitudes and speeds at which these aircraft operate. Additionally, since they do not require the extreme heat levels of jet engines, integrating hydrogen fuel cell systems is much easier. The engineering approach is equally impressive in its simplicity. Fuel cells generate electrical energy. Electric motors power the propellers, and hydrogen stored at -253 degrees Celsius serves as the energy source. There is no combustion process, no emissions, just clean electrical power derived from the most abundant element in the universe. The second concept was a turbofan model capable of carrying 120 to 200 passengers up to 2,000 nautical miles. This aircraft directly challenged the heart of commercial aviation. The narrow-body aircraft market was dominated by the A320 and Boeing 737. However, these engines bore no resemblance to any engines currently in service. Instead of kerosene, they were specifically developed to burn hydrogen directly. The combustion rate, materials, and all thermodynamic processes were designed from scratch. There is a fact that many people are unaware of. Hydrogen burns at much higher temperatures than jet fuel. We are talking about flame temperatures exceeding 2,000 degrees Celsius. This required entirely new materials, revolutionary cooling mechanisms, and completely different engineering strategies. Unlike fuel cell designs, this turbofan concept would produce only minimal nitrogen oxide emissions during hydrogen combustion. While still far more environmentally friendly than traditional aircraft, this was a phased approach, not revolutionary, but evolutionary. And then the most radical concept emerged: the hybrid wing body, 200 passengers and a range of 2,000 nautical miles. But to call it revolutionary does not fully reflect its significance. This design challenged the aircraft design approach that had been valid for over a century. There is no longer a cylinder with wings attached to the sides. Instead, the wings and fuselage merge seamlessly to form a flying wing that carries passengers. Why such a radical change? Aerodynamic efficiency. The hybrid wing body could achieve up to a 20% increase in efficiency compared to traditional designs. However, there is another critical issue: hydrogen storage space. Liquid hydrogen requires enormous tanks with exceptional insulation. In a traditional aircraft, finding space for these tanks while maintaining balance and safety is nearly impossible. But with the winged fuselage, there is an immense internal volume to work with. The passenger experience would be at a level never before seen in commercial aviation. Spacious cabins, potentially multiple decks, and entirely new seating configurations. This wasn't just a new airplane, it was a new way to experience flight. Now, the story reaches a critical turning point. In early 2025, Airbus made a strategic decision that surprised many industry experts. Instead of pursuing three concepts simultaneously, they decided to focus on a single four-engine fuel cell-powered aircraft. This new design combines the strongest features of the three original concepts while also considering practical production and operational realities. Think of it as a synthesis of their research. It takes the fuel cell efficiency from the turbojet concept, the passenger capacity concept from the turbofan concept, and the innovative design philosophy from the hybrid wing body concept. So, what makes these aircraft so special? Let's take a closer look, because this technology is truly fascinating. At the heart of Airbus's new approach is fuel cell technology. However, we are not talking about fuel cells used in automotive applications. We are referring to systems designed to operate at 40,000 feet altitude and produce megawatts of power, meeting aviation standards. Here's how it works. Hydrogen from cryogenic storage tanks combines with oxygen from the atmosphere inside the fuel cells. This produces electricity that powers electric motors driving the propellers or fans. The only byproduct is clean water. In 2024, Airbus achieved a significant milestone with Elring-Klinger by successfully testing an iron pod fuel cell system that generates 1.2 megawatts of power. That's enough electricity to power approximately 1,000 homes, an extraordinary achievement for aviation fuel cells. Perhaps the greatest engineering challenge is storage. Liquid hydrogen must be stored at temperatures just 20 degrees above absolute zero, or negative 253 degrees Celsius, where molecular movement is nearly frozen. This extreme cold, close to the universe's deepest freezing temperature, requires incredibly sophisticated tanks to keep hydrogen in liquid form and ready for flight. To put this into perspective, it takes approximately 400 grams of liquid hydrogen to store the same amount of energy as 100 grams of jet fuel, and all of it must remain colder than anything currently used in commercial aviation. Imagine boarding one of these aircraft. What would you notice? First, the absence of sound. Electric motors operate much more quietly. Airport operations would also change. You would no longer have to wait behind planes spewing exhaust fumes. The most significant change would be psychological. You would be traveling knowing that zero carbon emissions were produced during your flight. This would offer a completely new experience for environmentally conscious travelers. Beyond the engineering challenges, infrastructure development is extremely expensive and complex. A major transformation of aviation's hydrogen infrastructure is needed. This is similar to the development of electric vehicle charging networks, but on a much larger and more complex scale. These aircraft are only as viable as the infrastructure that supports them. Airbus has launched a program to develop hydrogen hubs in collaboration with major airports. We are talking about infrastructure that does not yet exist, such as hydrogen production facilities, cryogenic storage systems, and specialized fueling equipment. While Airbus is leading the way in hydrogen, it is not alone. Boeing is focusing on sustainable aviation fuels, while new companies are exploring battery electric solutions. This competition is accelerating innovation in aviation. Different approaches are complementary. Batteries for short routes, hydrogen for medium distances, and sustainable fuels for long distances. Let's be honest about the timeline. In February 2025, Airbus acknowledged that bringing hydrogen-powered aircraft to market would be more challenging than originally anticipated. The original 2035 target has been pushed back to the late 2030s. This is the result of a responsible engineering approach. Despite misleading reports claiming the cancellation of the ZeroE program, Airbus has confirmed that the program is continuing. Of course, this will happen with adjustments to the timeline and budgets. The physics and technology are working, as proven, but engineering integration and infrastructure development require more time. From an environmental perspective, these fuel cell-powered aircraft produce zero carbon emissions during flight and emit only water vapor as a byproduct. When powered by green hydrogen produced from renewable energy, they can reduce aviation's carbon footprint by 50 to 80%. Hydrogen aircraft will be more expensive initially, but they could become economically attractive in the long term. Maintenance costs could be significantly reduced because electric motors have fewer moving parts. Increasing carbon taxes and scaling up hydrogen production will shift the cost balance. Of course, there are challenges. Energy density remains a fundamental issue. Hydrogen requires about 4 times the volume of jet fuel for equivalent energy. Safety concerns and cost barriers also exist. However, these are not insurmountable. In 20 years, the planes flying past you will be powered by the most abundant element in the universe and leave only water vapor in their wake. This future is no longer a question of if, but when and how. Companies like Airbus are working every day to make this happen as soon as possible. If Airbus succeeds with ZeroE, the impact will extend across the entire aviation industry. Other manufacturers are accelerating their own hydrogen programs. Suppliers are investing in hydrogen-compatible components. The aviation supply chain is transforming. Working with cryogenic hydrogen and fuel cells requires new skills. Airbus is developing specialized curricula in partnership with universities around the world. This creates extraordinary opportunities for young engineers. Just as jets revolutionized air travel in the 1950s and 60s, hydrogen power could trigger equally profound changes. With reduced operating costs, new routes could become economically viable. Regional connections could improve significantly with quieter, cleaner aircraft subject to fewer environmental restrictions. The entire economy of air travel could change in ways we can't even imagine. While previous aviation revolutions were driven by performance improvements, this revolution is driven by necessity. The need to meet the growing demand for air travel while making aviation sustainable for future generations. Today's traditional aircraft represent incredible achievements in engineering. Combined with sustainable aviation fuels, they will remain very important for decades to come. However, they may represent the past rather than the future of aviation. The aviation revolution is coming. The physics works, the technology is available, the infrastructure is being built, and regulatory frameworks are being developed. It won't be easy, it won't be fast, and it won't be cheap, but it will happen. What do you think? Are you excited about the future of hydrogen-powered aircraft? Or do you think other technologies, such as sustainable aviation fuels or battery electric systems, will lead the way to decarbonizing aviation? Subscribe and like us to stay up to date on all the latest innovations in the aviation industry. Keep your eyes on the sky.